If we have more than one term in the denominator, it can be really rough to rationalize it unless we have a plan. So looking at this expression, 7 over 3 minus root 5, we might look at that and think, well, if I multiply root 5 by another root 5, I'll get a perfect square. That'll cancel out. Will that rationalize my denominator? Let's see what happens. So I've got 7 over 3 minus root 5. And I'd like to multiply my numerator and denominator, each by root 5. In my numerator, that'll give me 7 root 5. That can just sit there. That's fine. In my denominator, though, I have to distribute that root 5. So I'll get 3 root 5 minus root 25. So I'll end up with 7 root 5 in the numerator and 3 root 5 minus 5 in the denominator. So did we successfully rationalize the denominator? We did not. Why not? Well, because we also had to multiply the 3 term by the square root of 5. There isn't actually any one-term expression that we can multiply by that will end up canceling out the square root in the second term without introducing a square root to the first term. We need to multiply by a 2-term expression, and what term that can be comes from our difference of squares identity. Remember, if I have x minus y times x plus y, that gives me x squared minus y squared. The middle terms, remember, the x times y terms canceled out when we multiplied those. And the reason that that's useful is if I have 2 positive real numbers, so 2 numbers that have nice square roots, I can define a pair of what are called conjugates. We have root x minus y and root x plus y. And the key thing about these conjugates is if I multiply them together, so root x minus root y times root x plus root y, well, that gives me root x squared minus root y squared, which is just x minus y. Remember, we assumed that x and y were positive, so they have square roots. The square root is 1 to 1, so if we take the square root and then square it, we do get our original number back. So what this says is, if we multiply by the conjugate, we get rid of the square roots. And that's what we're going to use when we want to rationalize a denominator that has 2 terms, one or both of which are square roots. If we only have one square root, that's fine. A rational number is a square root of something after all. So for example, the 3 minus root 5 that I have in this denominator, its conjugate is 3 plus root 5. So to rationalize this denominator, I have my 3 minus root 5 in my denominator, 7 in the numerator. I want to multiply the denominator by 3 plus root 5. I also have to multiply the numerator by 3 plus root 5. Okay, according to my difference of squares identity, this is going to be 3 squared minus root 5 squared in the denominator. And I'm going to leave my numerator factored until I see what my rationalized denominator actually is. So 7 times 3 plus root 5 is my numerator. So 7 times 3 plus root 5 over 9 minus 5. Right, 3 squared is 9. Root 5 squared is 5. That's going to be 4, which I'm not going to be able to simplify. So I'm going to go ahead and distribute in the numerator. 21 plus 7 root 5 all over 4 is what I get when I rationalize that denominator. So notice we only defined this conjugate for a sum of one or both square roots. We can play a similar game for higher order roots by using the appropriate identities. So if we wanted to do something with a sum or difference of cube roots, we would use the sum or difference of cube identities, for example. In this class, we're going to limit ourselves to denominators that contain a sum or difference of square roots. So you don't need to concern yourself with the other identities for now. But be aware that this is a game you can play for any roots you want.